Hello everyone, this is Poornima Deepthi working as an assistant professor in the Department of Electronics and Communication Engineering at MLR Institute of Technology. Today I will be explaining the concept how to write programs in 8086, and the overview of today's concept is how to write the programs depends upon the array logics and string manipulations, how to write programs in string manipulations for 8086 microprocessor. Coming to the first program, here the arrays. What are the arrays? Number of data present in a single memory location. So here, how to perform arithmetical operation between the number arrays. So in these programs, I have already told you that in microprocessor, the memory is divided into different segments. So out of those segments, I've been using only two segments, data segments and code segments. So the data segment is used to keep the values of the data present in the programs, how to manipulate the data, and the code segment is used to execute the actual code. So here in this particular data segments, two arrays I have been taking. The first array is the data present in this particular arrays will be stored like this. If I am considering the address of that particular memory location randomly, second number, this is the offset value, this is the number 1 arrays, this is the number 2 array. So here 0, 2, 0, 5, 0, 3 and 0, 6H. Here 1, 0, 1, 2, B5, 2, 5 is the data present in this particular memory locations. Now coming to I was initializing AX with 0, BX with 0 and CX count with 4. Why we need to keep count as 4? Because here I was taking 4 numbers in each array group. So to perform addition or subtraction or any arithmetical operation between the arrays, you need to keep count the number of the numbers present in that particular arrays. Here I was taking 4 numbers in each array group, so that's why I'm keeping count as 4. So coming to the SI, index register is holding the offset value of number 1. What is the offset value of number 1? Here 1000, and the DI register is holding the value of number 2 offset. Here the number 2 offset is 2000. Now in this particular instruction, AL register is having the data present in the SI register's address. What is the address present in SI? 1000. So what is the data present in that particular SI location? 02. So now 02 will be moved to AL register. Next, here you can perform any addition operation or subtraction operation or multiplication division operations. Here add AL. So the data present in DL will be added with the AL register. What is the data present in DL? So here it is said that DL register is having the data present in the address location of DI. What is the address location present in DI? 2000. So what is the data present in 2010? So DL is having 10, AL is having 02H. So we will perform addition operation between AL and DL. So 02 will be added to 10. So what will be the output? 12H. This 12H output will be present in AL register, as the destination register here is a AL register. So this register will be holding to BX indirectly. So this is another memory location. So the output will be present in this particular memory location as 1. Yes, fine. Now the two numbers in the starting arrays, starting numbers in the two arrays have been added. We need to move to the second number in each array. How we will move? So here, after performing addition and addition or subtraction or any arithmetical operations, increment SI. The SI, the address present in SI will be incremented. So now SI will be incremented to 1001, and next increment DI. DI will be incremented to 2001. Now decrement CX. Before, as I already told you, CX register is having the count 4. Already we have performed one operation between our numbers. So it will be decremented by 1. So the count is 3. If we need to check whether the count is 0, no, count is not 0. So it will move to the jump if not 0. J and Z, jump if not 0. So it will check the CX register. If it is not 0, it will move back to the label back. So it will move. So now the data present in 1001, which is nothing but 05, and the data present in 2001, which is nothing but 12, will get added, and this particular data will be stored in that memory. And next again, SI will be decremented to next location, DI will be decremented to the next location. Now the CX register will decremented by 1 because 2 digits in particular arrays have been performed. So CX register, it didn't get 0. So it will again perform the same operation. So what is that? 03 and B2 will get added, and the output will be stored here, and again SI register and DI register. So this loop will execute until the CX register will get 0. So if the CX register is getting 0, then it will move to the int 03H codens and end starts to terminate the program here itself. So this is how addition and subtraction operations are performed in the arrays. So coming to the ascending and descending order. Before going to this particular concept, I would like to explain the concept behind the programming I have written. Here I have taken the bubble sort concept. So how bubble sort concept will arise? So let us see. Here how many numbers I have taken? 52, 52H, next 30H, 62H, and 42H, 17H. These are the numbers. So how we need to identify ascending order or descending order. Ascending order means the numbers with lowest to the highest numbers, and the descending order means highest to the lowest numbers. First we need to perform the ascending order. So how to perform the ascending order? It is a simple that we need to compare two numbers. First, the bubble sort operation begins here. 52 will be compared with 30. If 52 is less than 30, then it's okay. If the first number is not less than 30, then we need to swap the numbers. 52 is greater than 30, but ascending order means smallest number will come first. So we need to exchange this number. So 30H and now 52H. So this will be the output. Next, this second number will be compared with the third number. So 52H is smaller when compared to the 62. So no need to exchange any numbers. This loop will be like this only. Now the third number will be compared with the fourth number. So yes, here 62 is greater than 42. So we need to exchange it. So 42H will come to its place and 62H here 17. Now the fourth number will be compared with the fifth number. So again 62H is greater than the 17H. So we need to exchange the numbers. So here ends the concept. So are we getting the exact ascending order sequence? No, we are not getting the exact ascending order sequence. How to get the exact ascending order sequence? The ascending order sequence here is we need to get 17 after the 30, 42, 52, 62. But here we didn't get. So this is these comparisons are internal loops, and to perform this whole thing next time, that is the external loop. There will be two loops. So now again this will be the input. We need to perform the same operation. Again first number will be compared with the second number, and we will get 30, 52. The again 52 will be compared with 42. So again it will exchange. We will get 42H, 52H. Again third number will be compared with the fourth number. 52, 17 means again it will get exchanged. So 17, 52. Again it will compare with 52, 62. Yes, it is okay. So this is the second time performing the external loop. Now again it will perform internal loop once again. So 30, 42 will be compared, it is okay. But 42, 32 will be compared, but it is not okay. So it will exchange. 17, 42, 42, 52. So the data will be same. So this is the fourth time we have, third time we have executing the external loop. Again, are we getting the output? No, we are not getting the exact output. So again, we need to perform the external loop once again. So every external loop, for every external loop, internal loop will be executed. So now this 30 and 17 will be executed. Yes, 17, 13 will be exchanged. 42, 52, 62. Yes, we have getting the exact ascending order sequence here. So how many times the external loop will be applied? This is one, first time, second time, third time, and fourth time. How can you say that after executing the 4 times the output will be present? So we can say that depends upon the numbers you have taken in the array. So here how many numbers I have taken? 5 numbers. So to compare 5 numbers, we need to have 4 comparisons. First number with second number, and second number with third number with fourth number, and fourth number with fifth number. So to perform comparison operations between n numbers, n minus 1 comparisons will be there. So in this particular example, I have taken 5 numbers. So to compare 5 numbers, I need to execute internal as well as external loops 4 times. That's why I keep CX register 4 and another register I have taken to keep the count as BX register. So BX register having 4, CX register is also having the 4 count. One is used to keep the internal loop running, and another one is having the external loop running. So how to perform this in a technical way, we will see. So the data present in SA register. So 52, 30, 62, 42, 17. Let us take any one offset addresses. I was taking 1000. So this is the location where the arrays have been stored. So coming to this instruction, AL register is having SA register is holding the effective address of number 1, which is nothing but 1000H. So AL register is having the data present in the address location of SI, which is nothing but 52. So now AL register is having 52 number. So this number, next increment SI. SI has been incremented. Previously SI is in 1000. So SI has been incremented. So it will get the value 1001. So what compare operation? Compare AL. AL value is 52 will be compared to the data present in the location of SI, which is nothing but 1001, 30. So 52 will be compared with 30. So next one is JBE, jump if below or equal. So if it is not greater, then it will jump to the register. To find out the ascending order, we will be using JBE instruction. To find out the descending order, we will be using JNBE, jump if not below or equal, which is nothing but the greater. So here we will be using JBE, jump if below or equal. It will compare the destination register with the source register, source value. So source operand. So 52 will be compared with 30. So 52 is greater than 30. Here what they told, below or equal. So no, it is not satisfying that condition. So the condition will be dissolved and it will go back to the next instruction. So what is the next instruction? ECHG is nothing but the exchange instruction. What the value of the register SI? SI value is nothing but 1001 is holding 30. 30 will be exchanged to the AL register. AL register is holding. So now AL register will have 30 value and the value present exchange. So the value present in AL register will be moved to the SI location. So here instead of 30 the value will be 52. Yes. Now what I am getting, the SI location here is 52. Yes, we can not directly exchange the values in the memory. So that's why we are using AL register. Now what is the next instruction? Decrement SI. So SI value will be again decremented and it will get 1000 location. Move the data present AL value. So what is the AL value? 30 will be moved to the SI location. What is the SI location? 1000. So now 30 will be moved to the this particular location. So here one time internal loop is executed. So see. Next decrement CX. CX is the internal loop and here BX is the external loop. Now CX will be decremented. It gets 3. So it is not 0. Again the internal loop will be executed. See, jump if not 0, back 1. Again back 1. So the second number will be compared to third number and the loop will be executed like this. Okay, this is the another second time. So it will perform the bubble sort and the outputs will be executed here in the format of 17, 30, 42, 52 and 62. So for ascending and descending order, we will be using the same logic, but the difference is here if we want to find out the ascending order, we will use jump if below or equal. If we want to find out the descending order, we will be using jump if not below or equal. That is the difference between the ascending order and descending order. Now coming to the next one. Here largest number and smallest number. As we all know that after performing the ascending and descending order, we can get the value directly. See, after performing ascending order, the highest memory location will having the highest data. So instead of writing again the other logic, you can directly use the same logic. If you see, the same program will be used apart from the last one. So if we are performing ascending order, what we will get? 17, 30, 42, 52, 62. So if we are performing ascending order operation, you can directly say that the last memory location, so SI memory location is having the largest number. So the data present in that particular SI location will be moved to the DL. So the output will be the largest number. So the same operation, use it for the ascending order. To find out the smallest number, you can directly say that the descending order. So after performing the descending order, what we will get? You can say. So after performing descending order, the last data present in the SI location, memory location will be the smallest number. You can move that particular smallest number. Else the remaining program is same. Okay. Good. Next, coming to the string program. So as you all know, string is a combination of characters. So here, first one is to find out the length of the string. So here the same concept, we need to store the string in memory location because one character will contain 8 bits. One character will take 8 bits to store. So it is impossible to store the complete string in your register. So the strings always be stored in the memory itself. Here str is the label where the string is stored. I was taking offset as 100H. This is the complete example. So I am taking offset randomly. Now what is the string? Here string is mentioned in 2 inverted commas. So complete. So dollar is the representation that string ends there. So dollar is the representation that string is ended there itself. So what is the string I have taken? one location, only one character will be stored, because to store each character we need to have 8 bits of location. So memory locations is of 8 bits, so each location can hold only one character. So this is how. Yes, dollar is also stored in one location. So you can count how many number of locations present in the memory, then you can say that this many. Now these two are used to initialize the data segment within the code segment. I was making AX register and CX registers clear to hold the output. So SI is having the offset of string. Here the offset is 100 location. So next AL register is holding the value present in the address location of SI. What is the value present in address location of SI? 1000 is nothing but I. So AL register is having I. So it will compare I with dollar symbol. Why? So dollar is nothing but the end of the string. So you can count how until end of the string. So you can count the digits present or the characters present in the string like that. So we can compare with dollar. If it is not equal, no, I is not equal to. So condition, what is the condition here? Jump if equal. No, not equal. I is not equals to dollar. So this condition will never get satisfied and it will move to the next instruction. What is it? Increment SI. So SI will be incremented to the next location and increment CX. Previously, we have already got the length as CX. CX previously is 0. So increment CX, it will get 1. Next, jump to X. There is no condition in this particular instruction. It will jump to the label X. Again, this instruction will get executed. Now, so the data present in SI location. What is the SI location now? 1001. This location N is present. So AL will be moved. N is moved to the AL register. So N is compared with the dollar. So no, it is also not equal. Again, SI will be incremented to 1002 and CX will be incremented to. And again 1002. D is compared with dollar not equal. Again it will be incremented and CX will be incremented. Next I, A will get incremented. And now what is the data present in 1005 location? So now the data present in dollar. 1005 location is dollar. Dollar is compared with dollar. Yes, both are same. So JE, jump if equal. This condition will be now satisfied and it will move to the label Y. What is the label Y here? To terminate the program itself. So what is the count here? 5. So INDIA. 5 characters are there. So how this is how we will find out the length of a string. Okay. Fine. Next, coming to how to display a string. As in the previous videos, I have already told you, like first we need to give the offset address of that particular string where it is stored. So here string is stored in str label name. So we need to LEA means load effective address. So display the string completely, we will be using DOS interrupts. Here if we wrote AL, no, it will not take it as a interrupt, it will take it as a register. So we need to specify the above given instruction is a DOS interrupt, then you need to compulsory write int 21h, then only it will represent the interrupts. These two instructions in combination will display the given complete string. Okay. Next, coming to the next program, here comparison of two strings. As I already told you, there is no need to compare each character of string with the other character. There is one instruction which can be continuously compare the two strings and you directly given the output, which is nothing but compare string byte instruction used in the string manipulations. Here the first one is MLRIT. So it will be stored like this, MLRIT. The second string is nothing but, here string 2 is also MLRIT. So here repeat equal. if it is equal, the first character. So how will perform? M is compared with M. So if it is equal, then only it move to the next location. L is equal, then it will move to the next. If anything is not equal, then it will jump outside of the loop and it will end itself. So first one here. So if you saw here, I was using 3 segment registers. First one is data segment, second one is code segment, and the third one is extra segment register. Why? Why? Because here I need to initialize 2 strings. So to initialize 2 strings, yes, you can initialize strings directly, but I need to compare it in 2 different locations. So that's why I've been using extra segment. So first string will be initialized in the data segment and the second string will be initialized in the extra segment. Why can't we initialize the 2 strings in the data segment? Yes, it can. We can easily initialize. See here, 1 string, 2. This is also string. Strings are equal also a string. Message to 3 strings have been initialized in the data segment. So what is the purpose of having extra segment? Yes, there is a question, because if we need to use compare string byte repeat equal instruction, the condition is CX register need to have the count and data segment used to hold the first string and extra segment is used to hold the second string. If you didn't understand this, please go to the concept of instruction set, in particular instruction set, string manipulation instructions. There I have already explained. The condition to write this particular instruction is the count should be in the CX register and data segment should hold the string 1 and the extra segment hold the string 2. No need to increment the locations, nothing is there. If we write compare string byte, the first string present in data will be compared with the string present in extra segment until count tends to 0 or the strings are equal. If it is equal, we can directly represent that the strings are equal. If it is not, we can directly represent the strings are not equal. So until now I have discussed how to write programs on arrays and how to write programs using string manipulation instruction, how to find out the length of the string, or how to display a string, or how to identify the 2 strings are given strings are equal or not. Thank you.